All right, good morning. Happy Wednesday. Um, Today, what I'd like to do is to continue talking about acids and bases. We have a couple of more issues to deal with in terms of acids and bases. And if we have time, we'll get into oxidation reduction reactions. So we'll see if we have enough time for that. We might have a little bit to be able to go through that. So we'll see how it goes. Okay. All right. So we were talking about acids and bases yesterday. And what we said was that we had these compounds, which are molecular compounds called acids. And there were two different ways to think about them. One is that it's some sort of substance that when you dissolve it into water, it forms the hydrogen ion, which is hydrated by water, and a counter ion, an anion, that is now separated from the hydrogen ion. But there's another idea of what an acid is, and that is it's something that forms the hydronium ion. So it can actually react with a substance like water, for example. And in that process, it transfers this hydrogen ion to the water molecule. So that leaves behind, again, the chloride ion. That's your counter ion. But now you get this new substance that has the water and the hydrogen ion, and we call that the hydronium ion. Effectively, we can think of it this way. The hydrogen ion up here is really just sort of a shorthand notation for what's really happening, which is the formation of the hydronium ion, both of which we could use in calculations of acidity if we wanted to know how acidic the solution was. Some people are familiar with the concept or an idea called pH, for example. pH is related to the hydrogen ion concentration. We'll talk about concentration later this semester. And the hydronium ion, same thing, essentially. We can use them interchangeably. So essentially what people will do is they'll say, look, you got the hydrogen ion. That's essentially the same thing as the hydronium ion, okay? This second equation here has certain advantages. It allows us to evaluate reactions that may not seem like acid-base reactions, but in fact they are, okay? So the other substance we said was what we call bases, okay? And bases, we said there were two groups of them. The first one were the ones where you had a group 1 metal like lithium combined with a hydroxide ion. So it's an ionic compound. And if we put it into water, it just dissolves because of solubility guidelines. So you get a metal ion and you get this hydroxide ion. And this is the key. If a substance goes into water and you form the hydroxide ion in any meaningful amounts, then we're talking about something being a base. So this lithium hydroxide would be a base. So the group 1 metals and the group 2 metals, those are the bases. However, we also said there was this second group of substances, which we called nitrogen bases. And the common example of that is ammonia. And that if you put them into water, what happens is you get a reaction, kind of like we have over here. So what ends up happening is the ammonia reacts with the water, but in this case, the water is actually transferring the hydrogen ion to the ammonia. So the result of that is you get this cation that's positively charged. This is called the ammonium ion. And then you lose the hydrogen ion, so the water now becomes what we call hydroxide. Okay, and again, the key to thinking about what a base is a base is a substance that forms hydroxide. So since this reaction forms hydroxide, we would claim that the ammonia is acting as a base, okay? So hydrogen ion, H+, hydronium ion, H3O plus. Of course, those are essentially the same thing. And then you've got this OH minus ion, which is called the hydroxide ion. Okay. So now let's take a look at an example on Alex where we're looking at a chemical reaction between an acid and a base. There we go. So if we take a look at this example here, predicting the products of a neutralization reaction, neutralization essentially means that one reactant is reducing the chemical activity of another reactant. Okay, so it's neutralizing its activity. So in this case, could say that an acid is neutralizing the activity of a base by reacting with it, or the base is neutralizing the acid by reacting with it. Okay. So acids react with bases. Generally, acids don't react with acids, and generally bases don't react with bases. There are some interesting reactions you can look at where acids will react with acids, but in general, acids react with bases and bases react with acids. Predict the products of the reaction below, that is, complete the right-hand side of the chemical equation and be sure your equation is balanced, okay? If you take a look at this example, it has an acid, HClO4, so that's one of those oxo acids we talked about yesterday. So there's your acid. And then you got KOH, so there's your group 1 metal, potassium with a hydroxide ion, there's your base. The acid-base neutralization often can be evaluated as a double replacement reaction, just like precipitation reactions. You think of each reactant as having two parts, a plus and a negative, switch partners, then you've got your equation done right there. Okay, so let's take a look. So we have HClO4, aqueous, plus KOH, aqueous. Okay, so think of it as having two parts. So you got the H plus, and then you got the ClO4 minus. So you got your positive and your negative. Same thing here, K plus and OH minus. Switch partners. So the way this works out is the H plus will combine with the OH minus, and the K plus will combine with the ClO4 minus, right? Positive to negative. Compounds, particularly ionic compounds, are positive and negative. So we wouldn't put the H plus with the K plus, they're not going to combine. And we wouldn't put the ClO4 minus with the OH minus, they're not going to combine. It's positive to negative. It doesn't really matter which order you put it in. I'm going to do the potassium with the perchlorate. So KClO4 minus, right? So it's K plus ClO4 minus. So there's your compound. And then you've got your H plus and OH minus. That's water, right? So let me put in little parentheses down here. H plus OH minus gives you water. That's an important equation to remember. So anytime you have an acid, you probably have an H plus. When you have a base, you probably have an OH minus. H plus OH minus gives you H2O. Okay, that's essentially what drives acid-base chemistry, is the formation of this water molecule. Water is it is reactive, but it is also stable in a sense. So any compound that is got this H plus available and another compound which has the OH minus available, they're going to likely react with each other to form this relatively stable water molecule. Okay, we can do states of matter. Water is a liquid. And we have potassium here. That's a group 1 metal, right? The group 1 metal compounds are soluble. So this would be aqueous. So in a sense, it's a little bit like a precipitation reaction. It's analogous to a precipitation reaction in that you're getting two compounds, one of which is dissolves into water, right? You get an ionic compound that dissolves into water, just like we did with the precipitation. The difference here is that instead of getting a solid compound to precipitate, you're going to get a liquid water here as your formed product there. Okay, so that's what's called an acid-base neutralization. Okay, let's take a look at another example. So this one is HBr plus, again, KOH, same one, same base. Okay. So what do? Break it up into two parts. So you got your H plus and your Br minus, K plus, OH minus. So the H plus goes with the OH minus. So there's your water. I'm going to put the water first here. Usually people put the water second, which is fine. I'll put it first here though. And then K plus and Br minus. So that's KBr. They have the opposite charges. Again, potassium is group 1A, so it's going to be soluble. So this would be aqueous. Okay. And that's a neutralization. So what is the way we would put this in words is we would say that the hydrobromic acid is neutralized by potassium hydroxide. Okay. And then out of that neutralization, we form water and potassium bromide. So it's often stated, this is actually common language, it's often stated that if you do an acid-base reaction, the acid, so acids, in general, they react with bases to form water and a salt. This is actually a definition of what a salt is. A salt is the product of the reaction between an acid and a base. One of the two products of a neutralization reaction. Okay, so if you take an acid and you react with a base, you're going to get a salt out of it. And so in this particular case, the potassium bromide is the salt. In this case over here, it's the potassium perchlorate is the actual base. I'm sorry, the actual salt. So salt, water, acid, base. Let's take a look at one more example. Okay, so this one looks a little different. HI plus BaOH2. So notice this one has two hydroxides. Okay. So that comes into play when we're talking about balancing equations. It's said in the instructions that you have to balance the equations. So we'll have to deal with that. So here's what we can say. Again, we have your acid here. This is clearly the acid. And then this is the base. Remember, barium is a group 2A. So 2A has a charge of +2. Well, the hydroxide only has a charge of -1, so you need two hydroxides for every barium. So same idea though. What you do is you take your H plus and you combine it with the OH minus, hydrogen ion plus hydroxide ion to give you water. But now we just have to be careful because now the barium has a charge of +2. The iodine only has a charge of -1 because this is in group 7A. So this one's -1, this is +2. So that means we need 2 of the iodines. It's actually iodide in this case. Solubility guidelines will tell us that this is soluble, okay? So again, you got your 7A, you got your 2A. So for that reason, you have to have 2 of these iodines. So now we can just go back and balance it. If we have 2 iodines over here, we got to have 2 iodines over there, okay? I'm sorry, I didn't show that too very well. Okay, and then now we can balance the hydrogens. We've got 2 hydrogens over here, and we've got 2 hydrogens over there. So if we put a 2 there, we've got 4 hydrogens on both sides. Okay, so again, this is a neutralization reaction. The hydroiodic acid is being neutralized by the barium hydroxide, acid plus a base, giving us water and a salt. This would be our salt over here, right? A salt is the product of an acid reacting with a base. Okay. And there we go. All right. So that's sort of a, introductory writing equations for neutralization. The next thing we want to look at, come over here, is getting back into thinking about what do we get when we put acids and bases into water. Okay, so let me show you this next example. It's kind of it's a big table of stuff you got to put in here. Okay. All right, so let's take a look at this one. It says identifying acids and bases by their reaction with water. Okay. And it's kind of busy here. This problem is it has a table with a lot of stuff in it. So let's kind of dissect it a little bit. It says here that some chemical compounds are listed in the first column of the table below, and each compound is soluble in water. Okay, so we got these compounds over here. So for example, this first one is sodium bromide, NaBr. The second one's sodium hydroxide. That's a base, right? HNO2, that's an acid, right? You got your H in the front, so that's an acid. This one's called nitrous acid. It's in our list from yesterday. And then this is one of the bases, one of the nitrogen bases that I talked about yesterday, methylamine, right? You got this nitrogen with the hydrogens, so that tells you it's a base. So this is likely a salt. This is a base. This is an acid. And then this is one of those nitrogen bases. What it says then is that when you dissolve them into water, here's what you get in the solution. You have ions and you have water, right? In each case, you have water there, right? Because if you are putting something into water, there's water in there, right? So you have water for each one. And then these are the ions that are being produced. Now, what they want you to do in this problem is to determine whether this compound, whether these compounds were molecular or ionic. Okay, so what we said yesterday was that acids are considered molecular. The nitrogen bases are also considered molecular. And then the salts are ionic compounds, and the bases that have hydroxide, right? So for example, NaOH, those are really ionic compounds. And so those would be ionic as well. Okay, so the first step is to determine whether something is ionic or molecular. The next step is then to classify it as being either an acid or a base, but more specifically, whether it's a strong versus weak acid or a strong versus weak base. And we didn't really talk about the difference between strong and weak yesterday. So we'll talk about that first before we do this problem, and then that will allow us to classify which of these to check off for them, okay? So let me talk just for a moment about strong acids and strong bases versus weak acids and weak bases. Interesting idea. Okay. So we'll start with the acids. Acids can be classified. It's a classification system here. They can either be called strong or they can be called weak. Now, the first thing to say is that there are these substances which we call strong acids, and I'm going to list them all, actually. Let's put them all down here. HCl, I'll separate them with commas, HBr, HI, HNO3, H2SO4, HClO4, and HClO3. Those are generally considered a list of, it's a list of what we would consider to be the strong acids. There's only, was it 7 of them there? There are other acids that we might classify as strong acids, but these are generally the ones that we put in that list. Weak acids are generally every other acid possible. So examples of that would be HF, HNO2, not 3, but 2. I'm sorry, not 3, but 2. H2SO3, H3PO4.
Shut up. Bad.
HClO2, HClO. And we could keep going on and on. There are many more weak acids in nature than there are strong. There actually aren't that many strong acids. HBRO2, H2S. So I'm just writing a list down here. You don't have to memorize that second list, but the first list, this one right here, I would memorize those. Those 7 acids are considered the strong acids. Okay, everything else would be weak. And so I'm going to write down here, and many more. Okay, so now let's talk about what the difference is. What's the difference between a strong and a weak acid? It comes down to electricity, interestingly enough. So you can do a little experiment. You can find these on YouTube and TikTok and all that kind of stuff. So if you do the following, if you take some water and put it into a cup, a beaker. So if this is distilled water, you can buy distilled water in the store.
Would you guys mind muting your mic, please?
I muted everybody, so it should be good. Okay, so if you have distilled water, and you do the following. You put in 2 wires. Okay. And then you put a battery. So we connect a battery into that. And then you put a little light bulb. So I'll put a little LED. There we go. Okay. So what will happen is, so here's your little light. What will happen is if you put those wires into the water, nothing will happen. You won't see anything happen with this electrical circuit. But if you dissolve a strong acid, so you pour some strong acid, it could be any of these 7 that I've listed in there. Okay, if you pour some of it in there, what will happen is that strong acid will conduct electricity. And strong acids dissolved in water conduct electricity very, very well. And what will happen is the electron current will flow through the solution, and this light bulb will suddenly turn on, and it'll be very bright. So you'll get a lot of conductivity through that solution. So what we would claim from that experiment is that strong acids conduct electricity in water. In fact, I'll write very well in water. So we call them strong electrolytes because they conduct electricity. Okay. So if we wanted to know whether something was a strong acid, we would do this experiment. But since that experiment has already been done many, many times, we now know that it would be these ones right here. Those are the ones that would be the strong electrolytes. If we were to do the same experiment, but put a weak acid in, So an example would be HF or H3PO4 or HClO, any of those weak acids. What we would find is that it would conduct electricity, but very weakly. We would see a faint amount of light coming out of the light bulb. So it is conducting electricity a tiny bit, but nowhere near the amount that the strong electrolytes or the strong acids were doing. So for that reason, we call these weak electrolytes. So weak acids conduct electricity poorly, right? They don't do a very good job of conducting electricity in water. So we call them weak electrolytes. Okay, so strong acids conduct well, strong acids, strong electrolytes. Weak acids conduct poorly, weak acids, weak electrolytes. Now, why is that? What is actually happening? From a relatively simple description, what we can do is we can say the following. If you have a strong acid, and I'll use HCl as the example, when you put it into water, it will form H plus and Cl minus. These are the electrolytes. Okay, the H plus and Cl. Electrolytes are the particles that conduct electricity. So H plus is an electrolyte, Cl minus is an electrolyte. Okay. Essentially what we would say is that if we were to put in a mole of HCl, right? So 6 times 10 to the 23rd molecules of HCl. What would happen is that HCl would dissolve to such an extent that let me put final, that HCl would disappear. You wouldn't have any HCl. What would happen is it would be converted into H plus and Cl minus. So after we dissolved it, we'd have a mole of H plus and Cl minus. One of each, in fact, 2 moles. So now we would have 2 moles of electrolytes conducting electricity. And that's why it conducts really well. Strong acids, it turns out, dissolve so well and ionize so well that they will conduct electricity very well. So we call them strong acids. On the other hand, if we were to replace HCl with a weak acid, and just to use a simple acid on this list, I'll use HF. So this is a weak acid. So there's your HF. If we were to put in 1 mole of HF, a little bit of it would ionize. A little bit of it would be converted into H plus and F minus. Not 1 mole, but maybe 0.01 moles of each of these. About 1%, right? 0.01 is 1% of 1. So you get about 1%. And for many of these weak acids, that's essentially what you get. You get about 1% or 0.1%, 0.2%. Very small percentage of it. So if you're only getting a small amount of these ions, what's going to happen? Well, there's only a little bit of ions in this solution to conduct electricity. There's some, but not very many. So what'll happen is it'll conduct just a tiny bit, and you'll get a little bit of light coming off of the light bulb. Okay. So again, generally we don't memorize the weak acids because there's so many of them, but we do memorize the strong acids because there's only 7 of them. And you'll note that 3 of them are the ones where you have a halogen, group 7A, and then you've got these 4 oxo acids that are over here. So those are 7 strong acids. So what we would predict then is that if we put one of these strong acids into solution, we would have a lot of H plus, and we would have a lot of, for example, Cl minus, and we would have a lot of Br minus if that were the acid. On the other hand, if we put HF into the water, we'd only have a tiny bit of H plus and a tiny bit of F minus. So it would be mostly HF. So it might dissolve in the water, but it wouldn't form ions in the water. Okay, very small amount of ions. Now, something similar happens with the bases. We have strong bases, which again are strong electrolytes. That's the key. And we have weak bases, which are weak electrolytes. So in general, the strong bases are lithium, sodium, potassium, rubidium, and cesium hydroxides, all of those 5. So group 1A, all of those group 1A metal hydroxides are strong bases. But some, not all, but some of the group 2 are strong bases as well. So they are strontium hydroxide. Actually, I'm sorry, I forgot calcium. Calcium is in there too. Calcium hydroxide, strontium hydroxide, and then barium hydroxide. So be careful with the group 2 metals because beryllium and magnesium are not in that list. Even though they are bases, they're generally considered bases. They're not strong bases. Okay. So it's these, what is that? 8, right? So it's just like the strong acids. There's some strong bases, but again, these are easier to remember because these are just the group 1 hydroxides, group 1A. And then these are the bottom of group 2A, the last 3. Okay. Now, what about weak bases? Well, generally speaking, so these are weak electrolytes. Generally speaking, the first group of those would be magnesium hydroxide. Okay, so that's, right above calcium. It's in the same column, but it's right above it. And it just turns out to be an issue of solubility. It turns out that magnesium ion is so attracted to the hydroxide ion, it just barely dissolves. It's just not that soluble. So it's an interesting compound in that it's a base, magnesium hydroxide is a base, but it's not a strong base. So for that reason, it actually has some medicinal qualities. You can purchase something called milk of magnesia. It looks like milk, but it has magnesium hydroxide dissolved in water. And what happens is it doesn't dissolve that well. So it does not form a lot of hydroxide ions on its own. But since it is a base, it will react with water. I'm sorry, with acids. It'll neutralize acids. So if you have an upset stomach because of acid reflux, what will happen is you can take some of this milk of magnesia. It's a suspension, it's an emulsion in water. You drink it, and then the magnesium hydroxide will react with the acid that's in your stomach and reduce the acidity of the solution. Okay, but it's not a strong base. Just owing really to it's just not very soluble. But the bigger group are the nitrogen bases. So these are the ammonia, the methylamine, the ethylamine, and then I talked about yesterday aniline, which is C6H5NH2. Anytime you see C6H5, that tells you it's a ring. So that was yesterday we were talking about. These are all weak bases, weak electrolytes. Okay. So the magnesium hydroxide, the reason it's a weak base, a weak electrolyte, is that if you put it into water, only 1% dissolves. Now, when it dissolves, what does it do? It forms magnesium plus 2 hydroxides. And essentially, in order for it to be a strong electrolyte, it's got to conduct electricity really well. So if you put it into water and only a tiny bit of it dissolves, you're only getting a little bit of these ions. So again, that light bulb will very dimly turn on. It's not very bright because there aren't enough ions to conduct the electricity really well. So magnesium hydroxide, being a weak base, merely just has to do with its solubility. The nitrogen bases, though, are a different phenomenon. The nitrogen bases, remember, in order to consider these a base, they have to actually react with the water, right? And when they react with water, the water transfers an H+, so you get this ammonium ion, and you get this hydroxide ion, right? The reason that this is a base is because you form a hydroxide. The reason it's an electrolyte is because you form ions that can conduct electricity. So what happens is, again, if you put in a mole of this, you're only going to get about 0.01 moles of these. Only about 1% forms ions. So since you only have a few ions in there, it's going to be very poor conductor. You'll get a little bit of dim light coming out of that light bulb, but it will not be particularly bright. So the nitrogen bases are weak bases. Magnesium hydroxide is also a weak base. Okay. So now we can classify these things a little better. So let's come back to the problem. Oops. Come back to that table here. Okay. Imagine that a few tenths of a mole of each compound is dissolved into a liter of water. So we're just putting a little bit into some water. The important chemical species that would be present in the solution are written in the second column of the table. Use the check boxes to classify each compound. So let's take a look at the first one, NaBr. Okay, if you look at that, you can see it's an ionic compound, right? So you have Na plus, Br minus, and H2O. So you have ions in there, right? You have sodium ions, you have bromide ions. What that tells you is you've got an ionic compound right there, right? Ionic compounds are when you have a metal and you have a non-metal. Well, these are the ions that are formed from that. So it's an ionic compound. That's pretty straightforward. The question is it an acid or a base? Well, there's no H plus in there. There's no H3O plus in there, right? Remember, H plus and H3O plus, we use them interchangeably. There's nothing like that. So it's not an acid or a base. There's no OH minus, so it's not an acid. It's not a base. So if it's not an acid or a base, then we wouldn't check any of these over here. It's actually a salt if you think about it. If you take sodium hydroxide and hydrochloric acid or hydrobromic acid, you'll get sodium bromide as your salt. But no hydroxide, no hydronium, no hydrogen ion can't be an acid or a base. In order for something to be an acid or a base, you got to have some hydronium, some hydroxide. Let's look at the second one. We can recognize this is a base right here, right? And if you memorize the strong acids and the strong bases, you'll see this is a strong base immediately, sodium hydroxide. But they actually gave you some information here. They said, look, in addition to water, you've got sodium ions and you've got hydroxide ions, right? So that right there tells you it's a base, the hydroxide. So we know it's either a strong or a weak. Now, in fact, if you have a weak base, you're going to have a little bit of hydroxide in there. So it's a little tricky. Is this strong or weak? Well, again, I would recommend just memorize the strong acids, memorize the strong bases. Sodium hydroxide is a strong base. So there you go, strong base. The third one, you've got a hydrogen in the front. So that's telling you it's probably an acid. So let's see, H3O plus, there you go, right there. That tells you it's got to be an acid. You've got the hydronium in there. Bases don't form hydronium, acids form hydroniums. So acids are generally considered molecular compounds, not ionic. And if you take a look, see how you have HNO2 in there? What that's telling you is that it's a weak acid, and here's why. If you dissolve a strong acid, all of the acid will be converted into H plus or hydronium and then the counter ion. But if you put a weak acid in, you're going to have 99% of it is going to be the unreacted acid. So the fact that they put HNO2 in there, that's telling you that it's a weak acid. So we would select a weak acid for that one. And then the last one, this is the methylamine, right? The methylamine, if you take a look, you've got the hydroxide, that's telling you it's a base. The amines are molecular compounds. They don't have any metals in them, so they're molecular. So it's a molecular base, hydroxide, you've got that. Is it weak or strong? Well, again, I tend to recommend memorizing that the nitrogen bases are weak bases, and then the group 1 and group 2 metal hydroxides are the strong bases. However, the fact that they show you that there's a large amount of unreacted methylamine, right? Some of this did not react. That's another clue that it's a weak base as opposed to a strong base. For the strong bases, you don't have any unreacted base. For the strong acids, you don't have any unreacted acid. So that one would be a weak base. Let's take a look at one more. So we did this one already. We did the HNO2. This one's ethylamine, right? C2H5NH2. So that's a molecular base. It's got that NH2 part. That's what you're looking for, the NH2 or NH3 that's in there. Again, they do tell you you've got the reacted form and you've got the unreacted form of the base. So if you have some of the unreacted form, that means it's weak. You do have some hydroxide in there, so it's a base. So that would be a weak base. And again, the nitrogen bases are considered molecular compounds. HI, well, this is when you've got the H in the front, so it's an acid. It's one of the strong acids, right? But again, take a look at the strong acids. You get the hydronium, fine, but there's no unreacted HI. And that's a clue that it's a strong acid. There's no unreacted HI, so that's a strong acid. Ki doesn't have any hydrogen in it at all, so it's probably not an acid. It doesn't have any OH, it's unlikely to be a base. It doesn't have any nitrogen, it's unlikely to be a base. But let's take a look. We got K plus, I minus. This is just dissolving a salt into water. Ki is just a salt. So it's an ionic compound and it's neither an acid nor is it a base. Okay. So let's take a look at the last type of problem in here. And this is similar to the one we did a little earlier, but it's going to look at it from the perspective of the hydronium ion. So let's take a look at this. Predicting the products of a reaction of a strong acid with water. Okay. Predict the products of the reaction below. That is, complete the right-hand side of the chemical equation and be sure your equation is balanced and contains state symbols, solid, liquid, or gas, or aqueous, after each reactant and product. So they put them for the reactants, you have to do it for the products, okay? So when you're talking about the reaction of an acid with water, okay, that's when you want to invoke the idea of transferring the H plus ion. And that's going to form a hydronium ion. Okay, so let's take a look at this one. So HI. And again, we're going to predict the products. So acid-base reaction, you get two products. I want to write this down, how this would have been different compared to the previous problem we did. For that one, we would react it with like KOH. So this was our neutralization reaction, right? In the neutralization, you have an acid reacting with the base. And that's where we said, look, you're going to get two products. You're going to combine the H plus and the OH minus to give you water. And then you're going to take the metal with the non-metal, and that's going to give you the salt. Okay, so that's the previous problem we did. This is what we're doing here. We're reacting with water. And the key to this, we want to talk about how it is that an acid produces an acidic solution, or a base, for example, produces a basic solution. An acidic solution is one where you have an acid dissolved in water. A basic solution is the case where you have a base dissolved into water. There's another term for basic, and that's called alkaline. So if you see the term alkaline, that's essentially a synonym for basic. So you have an alkaline solution, a basic solution. In this case, we're going to take the HI and react it with water. Now, here's what we would claim. An acid can react with water by transferring the H plus to the water. So I'm going to write it with a little arrow here. The H plus, this hydrogen, is going to get transferred to the water. Now, if we come back to what we talked about yesterday, even though acids are considered molecular compounds, in a sense, they have something in common with the ionic compounds. They act in a way as if they have two separate ions there. So if the H plus is going on to the water, what you're left behind is the I minus. Okay, so you're just going to have I minus. And then the H plus is going to get added to the water. So what does that mean? When you transfer an H plus to water, what you get is H3O plus, our hydronium ion. Okay, so the second product here, or first, depending on which order you want to put it in, would be H3O plus. If something is charged, it's aqueous. Okay, so H3O plus, because it has a positive charge, would be aqueous. Iodine, because it's negatively charged, it would also be aqueous. Okay, so those are both aqueous. Okay, so this is showing us, we called it yesterday, we called it the Bronsted-Lowry. The Bronsted-Lowry is this idea that you consider an acid as being a substance which transfers H plus to another reactant. So this is what's called a Bronsted-Lowry acid. The Bronsted-Lowry base was a substance that accepts the H plus. So what's kind of interesting about this is that according to this definition, the water is actually acting like a base. It's accepting the H plus, so it's got to be a base based on that definition. And so water, it turns out, can be considered a base if you mix it with an acid. Okay. Let's take a look at another example.
Hey, Professor, do you have to put the charges in your answer?
Yeah, the charges are important because the difference between I and I minus is huge.
Okay, got it.
Yeah. Let's see. I'm sorry. Over here. I'm going to see if I can find one with a polyatomic ion. Here's one with a polyatomic ion. So let's stop share that one and bring this one up. Okay, there you go. So here's same idea, HClO4 aqueous plus H2O, right? So in this particular problem, it's reacting the acid with water, okay? So the idea here is that we're treating the water as a base. It's going to accept an H plus. So the way you recognize that is that if you see an acid, if you see the formula for an acid and it reacts with water, then you know to transfer the H plus to the water. Okay, acids transfer H plus to water. The alternate or the opposite of that, if you want to call it the opposite, is what happens if you put like ammonia into water, the base into water. Well, then it actually goes the opposite direction. The water transfers the H plus to the base. So the water in that case is acting like the acid, interestingly enough. So let's take a look at this one. It's HClO4. So the only real trick here is just to sort of see what the formulas are. So HClO4, aqueous plus H2O, right? Okay. So you recognize this is an acid, right? We have that list of the strong acids. This is one of the strong acids. HCl, HBr, HI. HNO3, H2SO4, HClO4, and HClO3. So those are their 7 strong acids. Okay. If you take a strong acid and you react it with water, what's going to happen is it's going to transfer the H plus to the water. We call that a Bronsted-Lowry reaction. Okay. So now the water plus H plus is H3O plus. There's your hydronium. And again, we said the hydronium is essentially the same thing as a hydrogen ion, it's H+. Even though the formulas look quite a bit different, chemically they behave the same. And then what we had was what's going to be left. Okay, well, what is going to be left? If you take the H+ off of the perchlorate ion, the only thing that's left is the perchlorate ion, so ClO4 minus. So yeah, ClO4, and then you're going to put that negative there. Okay. This is called the perchlorate ion. Okay, and there's your hydronium ion. Okay, and then this would be a Bronsted-Lowry reaction. Okay, the alternative way of representing this reaction would be to say, hey, we're just going to take HClO4 and we're going to put it into water, and it's going to form the hydrogen ion and the perchlorate ion. Okay. This is referred to as the Arrhenius model, which is just saying that when you put an acid into water, it forms the hydrogen ion and the counter ion, in this case, the perchlorate ion. But in a sense, these are all, these two alternative forms are really getting at the same point, which is that when you take an acid, what you're going to get is this chemically active species. In this case, we call it the hydrogen ion. In this case, we call it the hydronium ion, right? So the Bronsted-Lowry, you're actually saying, no, it's actually reacting with water. It's an alternative way of thinking about the same process. This one, it turns out, is more accurate. When we do studies of what's actually occurring in water, it's not the case that these acids just break apart and form H+ and ClO4 minus. They don't really do that. What they do is they actually react. You can actually do molecular dynamics studies and see that, oh, they're actually reacting with the water, and now the water has more hydrogen than it had before, and it now has a positive charge. And so this is really what's happening. So historically, what we do is we teach this first, and then we say, no, in fact, this is actually what's happening. But you want to be able to do both. You want to look at it from the perspective of the hydrogen ion, but also from the perspective of the hydronium ion. Okay. So H3O+ is essentially the same thing as H+ plus H2O, right? Those two will combine with each other. They'll collide and form this hydronium ion. Okay. All right, do that today. Okay, so that I think is actually the last problem, the last type of problem that we do when it comes to acids and bases, right? There's 5 different types of problems, 5 topics, we'll call them, right? And so that's it for the acids and bases. What will happen is if you go on to take the next course, Chemistry 1200, that's where we talk about pH. So pH is a measure of acidity. So what happens is if you take a strong acid and you dissolve it into water, it forms the hydronium ion. And that hydronium ion makes the solution acidic. So we would say an acidic solution is one that has a lot of hydronium ion. Likewise, a basic solution would be one where we dissolve a base and we have a lot of hydroxide ions. A basic or alkaline solution has hydroxide. So you can actually quantify that. We're going to talk more about concentrations next week, but the idea is you can quantify how much hydronium you have, and you can measure it. There's actually devices we can put into water and measure how much hydronium ions are in that water, or how much hydroxide ions are in that water. And so we quantify that through something that's called pH. So pH is a measure of how much hydronium ions are in the water. It also tells you how much hydroxide is in the water, but you have to calculate that. So that's something we cover in Chem 12. We go through the whole thing with buffers and mixtures and titrations, and we calculate pH and do all those kinds of fun things in there. It's some nice logarithmic mathematics, okay? But for this course, all we're really doing is we're introducing the concepts of what an acid is, what a base is, what a strong acid is, what a weak acid is, strong base, weak base, nitrogen bases, the hydroxides and all of that. We're just sort of classifying it and writing equations out. Okay. It turns out this hydronium ion is very special. It has the ability to do all kinds of interesting things, and that's part of the reason that we are so interested in acids and base reactions. Likewise, the hydroxide ion also is capable of doing some very interesting things. These are small particles that have charges. And when you put a charge on something, that gives it some reactivity and some activity that it can undergo. But not just that, the hydroxide ion and the hydronium ion actually have a particular type of chemical bonding in their structures, which is called covalent bonding. So the hydroxide ion has this covalent bond and a charge that also gives it properties that are different from ionic compounds. It gives it the ability to form chemical bonds to other substances. Likewise, the hydronium ion has these covalent bonds, but it also has a positive charge. And we represent these covalent bonds with lines, okay? And so we'll talk more about those covalent bonds and the structures of these ions later in the course when we get to chapter 8 and 9, really at the end. It's sort of the last things we cover. But those covalent bonds, along with the charges and the fact that they're small, gives them all sorts of reactivities that are pretty powerful. Okay. So let's do this. We don't have much time. So tomorrow we'll be focusing on reduction oxidation reactions, but let me just give a 3 or 4 minute intro to this. So we're going to call this is section 4.4. We're going to call them your textbook calls them oxidation reduction reactions. Okay. We generally abbreviate that as redox, reduction oxidation. So redox reactions. Okay. And redox reactions are very important in terms of energy. They are associated with large changes of energy. So when we study chemistry, we don't just study the transformation of atoms to form new substances. We also look at energy. So when we get to chapter 5, we're going to talk about energy more, but redox reactions are associated with very large changes of energy. So batteries, fuel cells, combustion reactions, those all involve reduction oxidation reactions. Biological metabolism is largely dedicated by redox reactions because we're talking about taking chemical energy in the form of food and transforming that into new materials, the body. And so breaking down compounds, building up compounds, those are generally associated with energy changes. So redox reactions are the reactions that are generally associated with that. Okay. So the idea of a redox reaction, very simply, is that if you have some substance, so it could be anything, just to make it simple, let's say it's a sodium atom. Okay, so here's a sodium atom. And it comes in contact with a non-metal. So this is a chlorine atom. Okay, so you have a metal over here. And you have a non-metal. So there are many different types of redox reactions, but this is perhaps the simplest type. What is observed is that metals generally do not hold on to electrons as tightly as nonmetals do. And so what will happen is an electron will be transferred over to the chlorine atom. So this is representing an electron here. Now, there are many different ways to represent electrons. One way is with a dot. We're going to talk about that in chapter 8. But in this chapter, the way we generally represent an electron is this way. a lowercase e with a negative superscript. Okay, so that's how we'll represent the electron here. But the electron is negatively charged and it will transfer from the metal to the non-metal. This is what's observed. And so when that happens, the sodium atom is no longer an atom. It's now an ion. It now has a positive charge. And this would now be called a sodium ion, okay, because it's positively charged. And likewise, the chlorine now has an additional electron. So it now has a negative charge, and we would call this a chloride ion. Okay. This is an example of a redox reaction. The sodium ion transferred an electron to the chlorine atom, thereby forming two new ions. So redox reactions are often associated with ions, right? Ionic reactions, essentially. Okay. And so we'll talk more about this. There's terminology in terms of what we call a oxidizing agent, a reducing agent. We'll get into all of that tomorrow. It's a rather involved discussion, so it may take us a couple of days to get through it. So we'll cover it tomorrow, at least the introduction to it. And then next week on Tuesday, we'll wrap it up. And then Wednesday, we'll get into molarity. We'll get into the calculations of concentration. And that will wrap up chapter 4. Okay. So have a great day and practice your acids and bases. And then we'll get into the redox tomorrow. Take care.
Professor.
Thank you so much. Professor, yesterday's lecture is on